Right, so this will be the first part of the derivation of the flexure formula for beam bending. So before we go on to this, as with torsion, we want to talk a little bit about the deformation assumptions using motion of human hands. So what we're talking all right. So the idea here is we initially have an element we're going to call beam. I think we all kind of know beams basically look like what they refer to, but for argue this something like this. Here's x-axis, y-axis, and then when we put bending on this, there's some moment that actually the beam actually. I'm going to draw a form. Bends up. And we can consider at each point lateral displacement. And we'll talk about it later. That'll be akin to how we describe the deformation, like a U or an angular twist. For now, let's talk a little bit about what goes on, assumptions that go on. So when this beam bends, well, this really isn't much of an assumption, but we consider that there's on one surface compression. That kind of makes sense. If you imagine just taking a paperback book, right, and you try to bend it up, you see compression on the top side, and then on the bottom side, you see tension. And that means somewhere in between, there has to be neither compression or tension. There's a point at which you switch from tension to compression. You label that. This is where there's zero axial stress. This is where stress, normal stress, is zero. On the tension side, normal stress is greater than zero. And on the compression side, normal stress is less than zero. Right? So there has to be some point at which that transition. That point is going to be called the neutral axis. That makes sense? It's neutral with respect to being neither tension or compression. All right. The other assumption that we make is that any cross-section, planar cross-section with undeformed shape, when it deforms, remains planar and also remains perpendicular to fibers along the x-axis. Does that make sense? So that's the second assumption. That, stay in a plane, form such that it stays in a plane, and that the planes, the formed planes, remain perpendicular. Okay? Now, so what we're not seeing is anything that might be like this, which actually is what happens in the attributed to shear. Normally, what you see is a perpendicular plane. Well, instead of everything staying plane, a lot of times what you see is actually like that. And you can see that if you take a thick book and like a phone book, and you can actually see those types of patterns. The other thing that you'll see, you can see that with most types as well, is that even if it doesn't, move out of the plane too much, a lot of times when it bends, even if it does say planar, it doesn't quite stay perpendicular. You can see that. You can always see that. So you see, if I bend it like this, you can actually see the edges of the book don't quite stay perpendicular at the max. If you try to force it to do that, it's actually quite stiff. Very difficult to do. Right? This softens the detail. This is what we call shear deformation. And we'll study that in the next chapter. But for now, our basic assumption is that it doesn't exist and that the planar sections remain planar and perpendicular. Now, where you see that idealization is very long, slender beams. Okay, these tend to support this idealization. As beams become thicker, they tend to, like that book, you tend to see the shear effects become dominant. Right? These two things here attribute to shear. And for slender beams, these shear effects are, deemed small. So what's a slender beam? Well, this is called 2C, and this is the length. Practically, if the aspect ratio is defined as L on 2C, if this is greater than 20, it's definitely a slender beam. Maybe you can get away with 10. Less than 10 becomes questionable how good these assumptions are. And obviously, that's affected by how good of an answer you want. If you want a coarse approximation, maybe even an aspect ratio of 5 is acceptable. If you want a very good calculation, and you have an aspect ratio of 10, you might want to consider shear to correct your answer. We'll talk about how to do that. Those are the assumptions we're making when we're talking about beam. Ends up, obviously, compression on one side, tension on the other side, and that means that there has to be an axis where there's neither tension or compression. That's the neutral axis. And then we're going to assume that the planar sections remain planar and perpendicular to that neutral axis. In reality, it tends to deviate from that, and that's associated with shear type of phenomena. But when we have very long, slender beams, aspect ratios of 20 or more, we can ignore those shear effects. Okay? So that's our assumption. Now let's do some math and see what that means. Okay? So here I'm going to draw a uniform beam segment. So there's my initial beam segment that's supposed to be uniform. So we don't know exactly where it is yet, but we're going to hypothesize, as we discussed before, that there is going to be some position after we bend it where the strain is zero, or the stress is zero. This is the neutral axis. Okay? We don't know exactly where it is yet. We call this position 1, because it's the bottom edge. That's the location of the neutral axis from the bottom. But I don't know what that is yet. Now, when it deforms, this is going to deform as follows. Put my thumb. This is a positive bending on this section, right? Bending over like that. And there might be more beam to right and left. So it basically is going to deform as follows. Exaggerate this. Put it off. This is very heavy deformation. You see this practically, right? Just draw a picture. This is, again, the deformed position of the neutral axis. So if we look at this, I can take these edges converge to some point center of curvature. All right, so that's the point where if I draw it, all these intersections intersect there. So this is a small segment. We're going to call this basically delta x. This is a segment that we can actually extend. So this beam bends up and forms this configuration. Obviously, extends out in this situation as well, right? Let's define another coordinate system from the neutral axis up. That's going to be my y-axis. All right? So y equals to 0. I'm going to call y equals 0. That's the location of the neutral axis. Although, and now we don't exactly know what it is, but we know the neutral axis exists, and so that's going to set up our description. If this is delta x, it bends to a region where you have a constant radius of curvature, or at least in the limit of delta x goes to 0. So that included angle we call delta theta. And now we can find the actual radius of curvature, rho. Rho is the radius of curvature. That's the radius of curvature. The radius of curvature is bigger, there's not as much bending, right? The radius of curvature gets smaller, more bending. So the radius of curvature of infinity is basically no bending, right? The smaller the radius of curvature, the more bending. We also will typically define the curvature, which is 1 over the radius of curvature. So it's the inverse of the curvature. It's the inverse of the radius of curvature. So in this case, smaller radius of curvature, this is the radius of curvature of 0, and this is a curvature of 0, the radius of curvature, as the radius of curvature gets smaller, the curvature goes up. Okay? All right. Now, we want to look at the strain. Well, really, I want to look at the stress on it. Right? So let's zoom in on this. Let's redraw this over a little bit bigger. Y-axis, Y direction. And now, from before, right? We know we have compression on one side and tension on the other side. We want to look at how that varies through the cross section. Well, if the planar sections remain planar, we can actually get the strain over that cross section. We can get the strain as a function of y. So if you think of the strain is going to be the change in length, the normal strain over the original. So if you look at some position, y, consider a fiber here. Okay? This is at some position, arbitrary position y. And that deforms, it's a little bit, it's going to go like this. Okay? So the change in length is this arc length over this original length. Okay? I'm sorry, minus this original length. Okay. So let's do that. So the original length, that's the original length. You can see from this picture that has to be the delta x. The original length is delta x. Now what's the new length? This length here. That's the L prime. All right. Well, it's going to be this distance here times delta theta. And this distance, this is the radius, this distance here is rho minus y. This distance minus y. Okay? So, that's the distance y. Neutral axis up here. So this distance, radius of curvature minus y. So that means L prime is rho minus y times d. All right. Well, I got a d theta and a dx. It's not so great. But actually, the dx and the d theta can be related. If you look at this fiber here, the neutral axis fiber, right? If you look at that neutral axis fiber, this distance here, that has to have an arc length of, that's where y equals 0. So that's just got an arc length of y. Right? But by definition, that's the point where there is no stretching. So this has to equal the original length, delta x. Right? What we're saying is that at y equals 0, the stretch length has to equal the original length. So that means that you can actually write this. The original length as y. I'm sorry. Rho, right? This length here is where y equals to 0, so you just get rho d theta, right? Here you set y equals 0. That's also the neutral axis. So there's no stretching there. So it has to equal its original length, which is dx. So what we're saying, rho d theta equals dx. So I can change here to rho. Okay? So now what do we got? The change in length is current length over the original length divided by the original. The current length, we're saying this is rho minus y d theta. The original length, we're saying is rho d theta. Now you can see all the d thetas cancel out. So I have a rho minus y d theta, this, minus rho theta over rho d theta. All the d thetas cancel out. This minus rho cancels out with that rho, positive. Now we're just left with minus y. Okay? So that means that the strain varies linearly as a function of y. So when we go up in positive y, the strain becomes negative and increases. And then when we go down here, it becomes positive tension increases as well. So the actual, if we were to plot the strain, it would look like this. This would be compression. The slope here equals to minus y. Regular curvature. Okay? Okay. All right, so that's our deformation pattern. All right? It's going to vary linearly. Compression on one side, tension on the other side. Obviously, if I flip the Benny-Bowman, side, which is tension, compression, flip. But there exists this neutral axis where it's neither in tension or compression. Right? Those are the important things. We don't know where that neutral axis is yet, and also we don't know how this strain relates to the internal forces. Okay? So remember, the other thing we're going to want to do is look at a little segment, very similar to what we did in torsion. You're going to have some strain and then therefore some stress distribution on one side. that is going to have to balance internal forces. E of x, normal force of x. Okay? So we don't know the location of the neutral axis. And we don't know how internal forces are related to this assumed deformation. So these are kind of like two unknowns. All right? So we're going to talk about that. Recap though. I think this is kind of important. And maybe you can argue that this was a pretty long-winded way of saying something that's pretty obvious. But we're going to make this bending assumption that the planar section remains planar and perpendicular. That basically shows us that we have to have a strain distribution which varies linearly from tension on the bottom side to compression on the top side for positive bending. What's that? There exists this neutral axis through the middle where it's neither in tension or compression. The length of the fiber remains unstretched at the neutral axis. From that, we're able to get the strain as a function of y. See, it's this linear relationship. Now, I don't know the radius of curvature. I don't know this distance here. That is the location of that neutral axis. And so what we're going to do next is find the location of the neutral axis. It's a little longer than I thought. So be it. Okay?